Okay, this video is the solution video for homework after lesson 2 of the waves unit, simple harmonic motion, HL only section. So the first question, a particle performing simple harmonic motion has a period of 0.5 seconds and an amplitude of 0.2 meters. Let's label this as t and that like xo. Find the value for omega for this motion. Well, omega is given as 2 pi over t. When you calculate 2 pi over 0.5, you get 4 pi radians per second. The particle's maximum velocity, well, VO is xo times omega, so substitution gives 0.2 meters times 4 pi radians per second gives 2.5 meters per second. Acceleration maximum is xo omega squared. Substitution gives 0.2 times 4 pi squared, calculates to 32 meters per second squared. The particle's minimum velocity is going to be 0. The particle's maximum acceleration will be also 0. The speed of the particle when it is 0.17 meters from equilibrium position. Now, realize that this is giving you a certain position, which is x, and it's asking for the speed. So, this is the brilliant place to use that formula. To find v, let's substitute omega, which is 4 pi, square root, the amplitude is 0.2, and we're looking at the position 0.17. When you calculate, you get 1.3 meters per second. Part G is asking for the time taken for the particle to reach a displacement of 0.10 from its equilibrium position. So now we're given a new x, and we want to find the time from equilibrium position. Now this is crucial because we're going to have to choose between this version and that version. So how do we do that? Now, if I use the sine function, I find the time when measured from 0 position, because if you substitute 0 for t, angle will be 0, sine of 0 is 0, so x equals 0. That means the sine function gives at t equals 0, x equals 0. Is that where we want to start timing? The question says from its equilibrium position, which means start from measuring when x is equal to 0, and that's exactly what we want. So what if I use the cosine function? I find the time measured using the cosine function from the amplitude, and here is y. So if I substitute 0 for t, that means my starting time t equals 0. Cosine of 0 is 1. That multiplies xo by 1, giving the value of x equal to xo. So that means if I start timing t equals 0 at x equals xo, the cosine function is going to give me the time from the amplitude, whereas the sine function will give me the time starting from equilibrium position, because t equals 0 gives x equals 0. Since the question wants the time measured from equilibrium position, we are going to go with the sine function. So let's substitute x. I put 0.10. My amplitude is 0.2 sine omega t. Next, I keep solving. 0.5 dividing by 0.1 by 0.2 gives sine 4 pi t. So 4 pi t is shift sine of 0.5. In radians, inverse sine of 0.5, 30 degrees, would be pi over 6. If you rearrange, cancel the pi, 4t equals 1 over 6, t equals 1 over 24, which is roughly 0.042 seconds. Now, before I go on to the frequency, I want to explain what would happen if we use the cosine function. Would it be really wrong to use the cosine function? Not really. So, I prepared this to show you that solution. So, if I use the cosine function, substitute x, amplitude, cosine omega t, half cosine 4 pi t, inverse cosine of half is now 60 degrees, which is pi over 3 in radians, equals to 4 pi t. Cancel the pi's, you get t equals 1 over 12, which gives about 0.083 seconds. Now, we got 0.042 seconds with the sine function. We got 0.083 with the cosine function. What that gives is, if this is the line for the simple harmonic motion, this is the equilibrium position, negative amplitude, positive amplitude. The sine function at t equals 0 has a value of x equals 0. So the sine function calculates the time as measured from equilibrium position, which is what we found, about 0.04. When I use the cosine function, since at t equals 0 this function has x equals xo, it starts measuring the time from the amplitude, which means reaching this point from the amplitude. So it gives us that time. The time taken from equilibrium to the midpoint of amplitude and the time taken from amplitude to the midpoint will not be the same. But here's the catch. Now, if you calculated that and realized that you have timed from the amplitude, you could actually calculate the correct answer. If the time from equilibrium to this point is 0.04, time from the amplitude to this point is 0.08, the total time between the equilibrium and the amplitude would be roughly 0.12. That's quarter of a period, because if you time the period, that will be 1, 2, 3, 4 steps. So from here to here, it's quarter of a period. If quarter of a period we calculated to be 0.12, full period should be about 0.48. In the question, we were given the time period to be 0.5. And this matches perfectly because this tiny difference from 0.48 to 0.50 is simply because of the rounding I did, which you probably realized when I explained. So you could subtract 0.08 from a quarter period to get the answer from equilibrium position. I wanted to show you that this works because I don't want you to think that using the cosine is wrong. Not really. It just gives a different time on the motion. Okay, let's go on with the last part of this question, asking for the frequency of the motion. Frequency is obviously 1 over t. Time period was given as 0.5, so 1 over 0.5 would give you 2 hertz. Okay, now let's move on to question 2. A particle performing simple harmonic motion completes 24 oscillations in 0.72 seconds. The amplitude of the oscillation is given as 0.2 meters, so let me write that over there. Calculate the period of the oscillation. This is a simple ratio. If 24 oscillations is completed in 0.72 seconds, one oscillation completed in t seconds. So, to find t, multiply 1 by 0.72 divided by 24, and that will give me the time period, which is 0.03 seconds. To find the value of the omega for the motion, I use 2 pi over 0.03, 67 pi radians per second. Okay, now that we know these two, the next part asks me to draw an acceleration time graph. So my y-axis is going to be acceleration in unit meters per second square, and the horizontal axis will be time. I can already label the time because I know now that one period is 0.03. So that's going to be 0.03. This will be half, quarter, and 3/4 of time. What I need now is the value of the maximum acceleration, so AO here and the negative AO here. I can calculate that using XO omega squared. XO is given as 0.2 meters, and omega we calculated as 67 pi. This is going to be squared. So when you calculate, you get that value for the maximum acceleration. So this number goes in there as the positive value and goes in there as the negative value. Now we don't know when we start the timing. We don't know if this is a sine, cosine, negative sine, or negative cosine graph. So 81 of them will do, and so I'll just go with the sine. So I'm going to do that and make sure I label those points, and that will be half the period. So the next question asks us to draw an acceleration displacement graph for the particle. The vertical axis is going to be the acceleration, the horizontal will be the displacement. The values, this was given in the question, and this is what we calculated above. We know from the defining equation of simple harmonic motion that acceleration and displacement are proportional, and they are always in negative direction. So this value is going to be 8773. This value is going to be negative 8773, negative 0.2, and this is positive 0.2, which gives me that graph as my answer. Okay, question number 3. A mass of 0.12 kilogram performs simple harmonic motion and completes 10 oscillations in 14 seconds. Let's find the period first. If 10 oscillation happens in 14 seconds, period would be 1.4 seconds. And we know that mass is 0.12 kilograms. So we are also given the amplitude of the motion is 0.1 meter. Calculate the maximum kinetic energy of the mass during its simple harmonic motion. Now, we know we're looking for the maximum kinetic energy, and we know kinetic energy is maximum at the equilibrium position. So I'm going to use the formula for kinetic energy as given in the formula booklet, 1/2 m omega squared xo squared minus x squared. Since we're looking for the maximum value, this term drops, and I'm left with 1/2. Mass is given as 0.12. Omega is 2 pi over t, and we're going to square that. And xo is given as 0.1, which will also be squared. So when you calculate, this gives 0.012 joules as the maximum kinetic energy. The second part asks for determine the maximum potential energy. Obviously, because the total energy is conserved, the maximum kinetic energy will be the same as the maximum potential energy. So this answer will be the same as above. Now we're asked to draw a graph to show how the particle's potential energy and kinetic energy change with time. This question will be answering the first question that I ask you to do at the end of lesson 2. So this will kill 2 birds in one. Because the maximum energy is 0.012 for both, let's start timing from when the object is at equilibrium. Now, at equilibrium, the object has maximum velocity. So its potential energy, elastic potential energy, will be a 0, and its kinetic energy will be at a maximum. This is when at t equals 0, x equals 0. That's the graph we're drawing. Now, let me put my little scale in here. This picture always helps. Kinetic energy is maximum here. Potential energy is maximum here and here. And we started timing right there. Let's say it doesn't matter which direction it's moving, so let's assume it's moving forward. Quarter period later, its kinetic energy will be a 0, its potential energy will be a maximum. So let's put that there. That's t over 4. At t over 4, it will be at the amplitude, so kinetic energy will be a 0 and potential energy will be a maximum. Another quarter period later, it will have come back to the original position, which is the equilibrium point, where its potential energy will be a 0 and its kinetic energy will now be a maximum. We are now halfway through the motion. The cycle will repeat. When it reaches negative maximum, its potential energy will be a maximum, which will be there, where its kinetic energy is a minimum, and when it completes one cycle, it's going to be potential energy minimum and kinetic energy at a maximum. So all the red dots are the kinetic energy and the pencil dots are the potential energy. When you connect those points, we end up with that for kinetic energy and this for the potential energy. If you want to add the total energy, will obviously be constant. That line will be the total energy at all points. Now, mathematically, since kinetic energy is proportional to velocity squared, and if velocity, we started timing from the equilibrium position, we started with maximum velocity, so velocity in this case would be a cosine function. The kinetic energy we expected to be a cosine squared function, which in this case, it is a cosine squared function of time. Please observe that in one period of time, this is 3 quarters, the kinetic energy is maximum twice. So this function completes 2 cycles, that is 1 and that is 2 in one period. Likewise for potential energy, completes 1 cycle and then another in one period of time, which is a sine squared function. Here's a little fun fact. If you mathematically think about the unit circle and the trig functions that you know of, cosine squared plus sine squared is equal to 1. Well, guess what? Their total energy, the sum, is a constant. So, moving on to the next part, draw with a scale to show how the particle's potential energy and kinetic energy change with time if the amplitude is doubled. So we had an XO originally, now we're dealing with twice that. Shortcut, because we're squaring the amplitude to calculate the maximum value, square of twice the amplitude is going to make the value of kinetic energy 4 times as big. So the graph will look exactly like this, but instead of having a maximum value, which was 0.012 joule, this maximum value is going to be 4 times as big, so it's going to be 0.048 joule, and the graph will be identical, which gives us this picture as the complete solution of this question. Describe and explain how and why this graph is different to the one in part A. To answer this question, you could simply say that the shape of the graphs will be identical, but the amplitude will be 4 times bigger because energy is proportional to the square of amplitude. Part C is asking for calculating the size of the maximum force acting on the particle in part A. Since it's asking for maximum force, I can relate that to the maximum acceleration. And maximum acceleration is omega squared xo. When you substitute the values for mass, which is 0.12 given in the question, omega was 2 pi over 1.4, and xo is given as 0.10. When you substitute all those values, you get 0.24 newtons for part A. For part B, you're supposed to calculate the size of the force acting on the particle in B. The only thing that changes in part B from part A is the amplitude becomes twice, which is directly proportional to the force. So doubling the amplitude will double the maximum force. Double 0.24, the answer is 0.48. Question number 4. The piston oscillating in a cylinder in a car engine has a motion that is approximately simple harmonic. Derive an expression to show the relationship between the maximum force F acting on the piston and the frequency F with which the engine rotates. So we want to find a mathematical relationship between F and the frequency F. So what I'm going to use here is what I have. In any derive, show that kind of question, you need to start with what is already given to you in the data booklet and end up with the relationship that is required. You're going to need to juggle some different formulas. You're going to need to be creative with the algebra and use what makes sense. For this case, to relate force to friction, I'm actually going to use what I used in the previous question, because since F equals m times a and F is mass times omega squared times x, to generalize now, not necessarily the maximum. In this formula, since we're trying to relate to the frequency, that is embedded in the omega. Omega is 2 pi over t, in other words, 2 pi f. So to find the relationship between force and the frequency, since I'm squaring omega for f, I'm going to take the square of this, and I can write f is proportional to f squared, because omega is proportional to f and force is proportional to omega squared. So force will be proportional to the square of the frequency. To sketch a graph to show force versus the frequency, force versus the frequency, this should obviously follow the pattern of y equals x squared, so a quadratic graph. It should look like that because it's a quadratic relationship. Explain why pistons are usually made from aluminum. So aluminum has low density, so the pistons have lower mass and less force is needed to move them. Also, force is proportional to frequency squared. The piston will be able to complete more revolutions per minute. It will be more powerful. Any words to that effect would answer that question. Okay, the only unanswered question from the activities I asked at the end of lesson 2 was the second question on the last slide, which asked to derive an expression for omega in terms of the spring constant K. So, looking at the formula booklet, you know omega is equal to 2 pi over t. And we also know that period of a spring is given as 2 pi in the square root m over k. Bringing those two together, if you substitute t in the omega formula, you get that. Cancelling the 2 pi's, you would end up with omega equals 1 over the square root m over k. Rearranging that gives you omega equals square root of k over m for the oscillation of a spring. Thank you. That's the end of this video. See you in lesson 3.